Hello ladies and gentlemen, we're going to do 7.2 Exponential Decay. Very similar to your lecture from yesterday, except now we are going to decrease instead of increase. Alright, yesterday we talked about exponential functions, so y is equal to a b to the x, and we said that they look like this with a y-intercept of 0, 1. So that is an exponential growth. Okay, so I'm going to write exponential growth. Today we're going to talk about exponential decay. Alright, the graph is going to look different. Now it's going to go this way. Okay, so it's still going to cross the y-axis at 0, 1. The equation is still going to be y is equal to a b to the x. The difference is for b, it's going to be 1 minus our percent. So b is usually a decimal. Okay? Back in the growth case, your b was 1 plus the percentage. So b was greater than 1. Okay? Alright, so that's the primary difference between our two equations. A is still going to be the initial amount. B is still considered, instead of calling it growth, we'll call it the decay factor. And x still represents time. So in essence, everything is the same. The only thing that has changed is b. Some equations might look like this. Y is equal to 10 times 2/3 to the x. Okay? So if I had that particular equation, if I did 1 minus 1/3, I would get 2/3. So this is actually my percentage of decay. Alright, so it would be 33%, or I could write it as a fraction 1/3. Okay? If I had y is equal to a negative 2 to the 3/4 raised to the x, the negative is still a reflection. This is less than 1, so I'm going to put less than 1 up there. And then this is a reflection across the x-axis. This is still a decay. My percentage of decay would be 1/4, because 1 minus 1/4 gives me the 3/4. Okay? I can translate this just like I did my other ones, so I could have y is equal to a, b, x minus h plus k. So virtually everything still looks the same. The only primary difference is b, and if you'll notice my graph is decreasing, it's getting closer and closer to 0. On this one, my horizontal asymptote would be y is equal to 0, because it will never quite get there, but it's trying to. Alright, so let's do our first example. Okay. So the first example says describe, oops, forgot the E, the transformations, and then graph. And remember, anytime that we graph, we want to label everything well. So your equation is going to be y is equal to 3 1/2 x plus 1 and then minus 2. Alright, the 3 is our initial value. It's also the vertical stretch. So 3 is going to be a vertical stretch. Okay. This tells me that it's decay, so I know which direction my graph is going. This is going to go left 1 and then down 2. Alright. If I graphed this, I would do it in my grapher to help me find the y-intercept. Okay, so I'm going to bring in my grapher and then I can sketch my graph. So if I bring in my y equals and I enter 3, and I'm going to do 1 divided by 2, and then I'm going to raise it, parentheses, x plus 1, and then outside the parentheses minus 2, zoom 6. Alright. My horizontal asymptote occurs at y is equal to negative 2, and your asymptotes always move with the vertical translations. So my horizontal asymptote is actually going to be y is equal to a negative 2. I'm going to just scoot this over for a second. So I'm going to draw -2, and that's my horizontal asymptote. That's the values that my graph is trying to approach but will never cross. The only other thing that I need to do now is find the y-intercept. So second, calculate value. I enter 0, and I have that it occurs at a -1/2. So right there, the -1/2 is going to be where it crosses. Whoop, and then, even though my drawing looks really bad, it will never cross the horizontal asymptote. Okay? All right, so now let's move on to another example. All right, so we're going to do a word problem, and I think I already have it written down. Lucky me. All right, in this one it says our snowmobile is going to cost $4,200, and it says the value of the snowmobile decreases by 10% each year. Another word for this is depreciates, okay, which means that it goes down in value. So A wants us to write an exponential model. B wants us to estimate the value after 3 years, and then C, estimate when the value of the snowmobile will be $2,500. This one is just like a problem we did in class yesterday. We will have to do this either graphically or in our table, because at this point you don't know how to solve for the variable when it's in the exponent position. So if I do A, I'm going to have y is equal to a b to the x. My initial value is the 4,200. My b, it's decreasing by 10%, so it's going to be 1 minus 0.10 and then raised to the x. And then if I just simplify that, I'm going to get y is equal to 4,200 times 0.90 raised to the x. Okay. All right. So that's my model, okay? And notice it's decay, and I know that it's decay because that's a decimal, it's less than 1. The B part then says estimate the value after 3 years. So I'm going to substitute a 3 right here in for my x. So I'm going to get 4,200 times 0.90 raised to the third. I'll do that on my handy dandy grapher. So 4,200 times 0.9 raised to the third, and I get that the value is 3061.8. So when I bought it, my snowmobile was worth 4,200, and after 3 years, that's a 0 by the way, my snowmobile is now only worth just a little over $3,000. So that's what depreciation does. It decreases in value. All right. The C part I'm going to scoot to the side a little bit. I'm going to write my model again. So the 4,200 times the 0.90 to the x wants me to find out what x is when the y value is 2,500. So I'm going to put the 25 here, and then the 4,200 here, 0.90 to the x. You really don't have the ability at this point to solve for x. We will in a few days. So what I'm going to do is graph the original equation and then trace the graph to find out when I get to 2,500. It will be an approximate, not exact, because I'm doing it in my grapher on the equation instead of by an equation. Sorry, instead of with logarithms. All right, so there's my handy dandy equation, and I'm going to do a graph with a zoom 6. All right. And I don't see anything, so I'm going to do a zoom 0, and here comes my graph. Notice it's decay, so it's decreasing. So now I'm going to use this button right here, the trace button. I'm going to use my right arrow, and notice I'm looking for the value of when y, so I'm watching my y value, gets close to 2,500, and that's probably about as close as I can get. So if you can see on my calculator, it says that y is 2508, which is pretty close. The corresponding x value is 4.893. So the time that it takes my snowmobile to be worth only $2,500, x is going to be about 5 years. Okay, because it's a little bit more than that, but a little bit less than the next number. So that's how I would find it. The other way to do it is to look at my table. So I'm going to actually go to my table, okay, and notice my x values are negative, so I need to go more positive. So I'm going to go down, and I'm watching the y values, and I'm looking for about when I get close to $2,500, and my y value is $2,480, so I would say that x is equal to 5. So I could either get it from my table or from the graph. Neither is very precise, so we will get another method to do this more precisely later. Alright, your next example, okay, says when a plant or animal dies, it stops acquiring carbon-14 from the atmosphere. Carbon-14 decays over time with a half-life of about 5730 years. So remember, half-life is when we talk about radioactive decay. The percent P of the original amount of carbon-14 that remains in a sample after T years is given by the equation. They give us the equation, which is very polite. This is a little bit different right here, and it's because we're talking about half-life. It was nice of them to give us that formula. It says what percent of the original carbon-14 remains in the sample after 2,500 years and then after 5,000 years. So this is just a calculator exercise. So if I do the first value, 2,500, I'm going to substitute it into my equation. So there's the half. My time is going to be 2,500 divided by 5730. In a half-life problem, I need to adjust my time for the amount of time that the half-life occurs in. So now let me show you how I do this on my calculator. I'm going to do 100 times 0.5. I did that instead of the fraction. Raised parentheses 2,500 divided by the 5730. Oops, sorry, I did it twice. And it takes, or sorry, there's going to be 73.903% of the original amount left after 2,500 years, which is a lot. That says almost 3/4 of the original amount is still left after 2,500 years. Then if I do the 5,000 years, substitute in my values, so here's the half, and then it's going to be 5,000 divided by the 5730. Because the only number that changed is the 5,000, I'm actually going to do second enter, bring that one right back up, and I'm going to do 50. So now notice I have everything politely done, and it was a little bit easier. The only thing that changed was the 2,500 went to 5,000, and now I have 54.616% left. So after 5,000 years, a little bit more than half of the original amount is still left. Okay? So that was pretty easy. So everything that you learned yesterday applies to what we're doing today. We're not going to do a compound interest formula differently, so that stays the same. The only thing that changed today was our B. So let me give you your problems. Okay. All right, first problem says to graph the function, and then of course you need to label the y-intercept, and then I want you to label the horizontal asymptote. And remember that that's always going to be an equation, so it will be y is equal to some number. Okay? Sorry, my paper's crooked. And your equation is going to be g of x is equal to 2 times 0.75 to the x. All right? The second one says tell whether the function represents exponential growth or decay. All right, and then you're asked to explain why. All right, so the first equation is going to be f of x is equal to 4 times 5 divided by 2 raised to the x. The second one is f of x is equal to 2 over 7 times 4 to the x. And then the last one of these is f of x is equal to 3 times 0.25 raised to the x. Remember, the growth or decay is determined by b. All right, and then we're going to end with a word problem. So I have a little bit of writing to do. When a person takes a dose of ibuprofen, so there's my I milligrams of ibuprofen, BPR. The amount A in milligrams, so we don't have to worry about any unit conversions, remaining in a person's bloodstream after T hours is modeled by the equation A is equal to I times 0.71 raised to the T. Find the amount of ibuprofen, PRO, it's a weird word to spell, okay, remaining in a person's bloodstream for a dose of 400 milligrams. Okay, I'm going to have to turn the page after 5 hours. All right, so these become your two critical values. I guess you can't see them, to substitute into your problem. All right, nice short video today, 17 minutes. I will see you tomorrow.